In the last video, we looked at vector arithmetic. We looked at vectors plus vectors, vectors subtracting other vectors, and vectors multiplying by a scalar. We briefly looked at vector multiplication. We mentioned that there are two types of vector multiplication. We've got the dot products and the cross products. So we're going to revisit that slide, and then we'll do some examples introducing both dot products and cross products. We introduced this slide in the last video, right? We said, let's say we have two vectors, a vector u and a vector v. And let's say it has an x component, a y component, and z component. Both of them have those components. And if we join the two vectors at the base, we define an angle theta. That's the angle between these two vectors. And we've talked in the past about magnitude. Remember, these are the symbol for magnitude of u, magnitude of v. And when we talk about dot products, right, all we do is we take each x components and multiply them together, add that to the y component product, add that to the z component product, AD plus BE plus CF. It gives us a scalar, a specific number. It's not going to give us a vector. Dot product gives us a scalar. So when we're interested in a scalar component, we use a dot product. Another way we can solve for this is multiply the magnitude of the u vector with the v vector magnitude, and then multiply it by cosine theta. And what we find is you can either just isolate the magnitude of v times cosine theta, or the magnitude of u times cosine theta. And what that really represents, what the dot product really represents, is the product of the two vectors if you project u onto v or v onto u, meaning you're looking at the product when both vectors are in the same direction. So some interesting things fall out of this, and we'll take a look at an example to show us this. Where the dot product gives us a scalar, the cross product gives us a vector. So we get this funky looking equation, and if the u and v vector have x, y, z components, the cross product is also going to have a x component, y component, and a z component. It also tells us, this equation also tells us we can solve for the cross product by determining which direction is normal to the plane that both the u and v vector lie on. So, for example, I don't know if you can see this well. All right, so I have these two markers right here, right? I can point them anywhere in space, right there, right? So I can point them anywhere in space. And if I put a piece of paper on the surface of this marker, these two markers, then that's the plane. If I go normal to it, if I put a pen normal to it, then that's the n vector. Now, we'll talk about how do you determine what's the sign, what's the direction, using something known as a right-hand rule. If you've taken physics, you might have learned about that. So this simplifies things. It's saying the magnitude of u times the magnitude of v times sine theta, the same theta that we defined earlier for the dot product, is the magnitude in the nth vector. Now the nth vector, n hat direction, right? It could be in the I hat or x direction, y or j hat direction, or z or k hat direction. Or it could be some combination of the three. For simplicity and just the introduction to cross products, we're going to look at cases where the n vector is equal to either the positive or negative k hat term, or the positive or negative z direction. And we'll use the right-hand rule to help us determine if it's positive or negative. So let's take a look at some example problems for first the dot products. Now we're going to take a look at the dot product using actual numeric values for vectors. We're going to use a baseline vector u that has an x value of 5 and a y value of 0. Now remember, it doesn't matter where I place my vector as long as I take 5 steps in the x direction and no steps in the y direction to show that relationship here. All right, so if I solve for the magnitude, obviously this is equal to 5 because there's no y component, so it's all going to be from the x component. I mean, let me introduce a second vector that we can take a dot product of. Right, so my second vector is vector v, has a y component of 3 and no x component. So I also know that this is going to have a magnitude of 3. I can draw right here, I can draw it anywhere, but it's actually easy. It's easiest if we draw the two vectors that you're taking the dot or cross products with a common base point. This way you can see the angles more clearly. Obviously one is going vertical and the other is going horizontal, so we're going to have a 90-degree angle right here. Now remember, the dot product is the product of the two vector magnitudes when one is projected onto the other. So what does that mean? So if this blue vector is projected onto the red vector, it's going to collapse along the horizontal. So it's basically asking, what's the x component of this vertical vector? Or alternatively, you can say, what's the y component of this horizontal vector? Now, I specifically chose my base vector to be 5, 0 so that it would be easy to see. But you can choose any kind, right? If it's pointing it like in this direction and you had this vector, it would be what's projected onto that surface. You could just rotate this whole screen and you get the same idea. It's just a little easier to look at it from this perspective. All right, let's take the dot product between u and v using first this equation and then this equation here. So the first thing we do is we multiply the x and y components. So 5 times 0 plus 0 times 3. That's going to give us 0, right? And it makes sense based on what we're talking about as projections. The blue part projected onto this red vector is 0. The red vector projected onto blue vector is equal to 0. And that's due to the fact that they're at 90 degrees. Okay? We can alternatively use this equation to solve for the dot products. So the magnitude of the u vector is 5. The magnitude of the v vector is 3. So 5 times 3 is 15 times cosine 90 degrees. Cosine 90 degrees is equal to 0. So this is also equal to 0. Note that if you change the order, if you change this to v dot u, you would still get the same solution. Let's take a look at another example. Here's another vector, vector w. This is basically taking this blue vector and rotating it 90 degrees, or I guess in the clockwise direction, 90 degrees. So it's pointing, has an x component of 3 and a y component of 0. So this is also going to have a magnitude of 3. If I try to take the dot product between u and w, what do we get? The projected component of this w onto this red vector is the full vector itself. So it's going to be different. So we get 5 times 3, 15, plus 0 times 0, 0. So it's going to give us a dot product of 15. The angle, and I chose a larger, a thicker red vector line just so that we can see the two vectors lying on top of each other. The angle between these two, because they're parallel, is 0 degrees. So if I use this equation now, the magnitude of the u vector is 5, the magnitude of the w vector is 3, cosine of theta, 0 degrees, is equal to 1. So 5 times 3 times 1 gives me 15, which matches right here. All right, again, if you swap the w and u vector, if you made this w dot u, you would still get the same solution. It does not, the dot product does not rely on order. All right, for the last vector, let's take a look at the z vector. We define an x component and a y component of 3, 3. So it's going to be angled. And so 3i hat plus 3j hat. This gives me a magnitude of 3 square root 2, right? 3, 3 is basically looking at this as an isosceles triangle. So u dot z is going to be 5 times 3 for the x component plus 0 times 3 from the y component. So 15 plus 0 gives me 15. And this is an angle of 45 degrees because of the isosceles triangle relationship. So if I use this equation here, I get 5 from the magnitude of u times 3 root 2 from the magnitude of z times cosine the theta value of 45 degrees. And remember, cosine 45 degrees is 1 over root 2 or root 2 over 2, same thing. So 15 times square root 2 from the magnitude product times square root 2 over 2 from the cosine theta value. Square root 2 times square root 2 gives me 2. 2 divided by 2 is 1. So this gives me 15. So a couple of key points to recognize from this slide. The dot products of perpendicular or normal vectors is equal to 0, as we saw here. The dot products of vectors that are parallel to each other is just equal to the product of the magnitudes. And then something in between is basically taking a look at the projected components. Don't mistake this as saying it's always the x component multiplied by the other piece. It only so happens to be so here because I chose this vector to be perfectly horizontal. So think about it as the projected component. Now, which method would you want to solve? It depends on what information you're given by the vector from the vectors. Obviously, it's a lot easier if you're given the vectors in this form to solve it this way. But sometimes you might be given the magnitude and the relationship between one vector and the other in a theta form. In that case, obviously, this is the equation you would want to use. But if you understand trigonometry, sine, cosine rules, you can always back out one or the other on your own anyways. Okay, so let's take a look at cross products. Remember, dot products go to scalars, and the order between the two vectors does not matter. In a cross product, you're going to get a vector, and the orders you're going to see does matter. So let's take a look at the same vectors, and let's see what the resulting cross product will look like. So we're going to look at the cross product now. Remember, the result of a cross product is a vector. How do we remember something so complex as listed right here? Well, one thing we can learn is the determinant. We're going to learn more about determinant in a future video, but for now we're going to use it for one specific case. So if I want to take a cross product, I want to remember this rule. I can draw a 3x3 matrix and tell it I want to find the determinant by drawing a vertical line on the left and right side of this matrix. This matrix is always going to be built in the same way. You write your basis vectors in the top row, I hat, j hat, and k hat. In the second row, you write your terms of your first vector, in this case u, so a, b, c. And then in the third row, you write the terms of your second vector, in this case v, d, e, f. Then you change this 3x3 determinant into multiple 2x2 determinants. And you're going to get an I hat term, you're going to get a j hat term, and you're going to get a k hat term. So this determinant right here is going to be this component right there. Now the next thing you have to look at is the signage. In front of your first term, you put a positive sign, and you alternate negative and then positive. So the j hat term is going to have a negative sign right there. Then you need to fill in the 2x2 determinants that you create. And the way to do it is very simple. For I hat, you cover up that first column. The remaining terms become your 2x2. So you cover up that first column, you get B, C, E, F right there. For the j hat term, you cover up the middle column, and then the remaining 4 go in here, A, C, D, F, right there. And then for k hat, you cover up the third column, and the remaining 4 show up right there, A, B, D, E. Okay, so now that you have your 2x2 determinants, now you need to determine what the scalar resulting from these 2x2 determinants are. And the rule is very straightforward. Again, you take the product of your diagonals and you subtract them. And you have to remember which one you put the negative sign in front of. You always start from the top left. So BF minus EC. BF minus CE times I hat. Then minus, you do the same thing here. AF minus CD. So minus all of that. So we get a minus AF plus, so minus minus or plus CD j hat. Then AE minus BD. AE minus BD k hat. Okay? So that's one way to solve for the cross product. The other way is similar to what we showed in dot products. We do magnitude products. In this case, instead of cosine theta, we use sine theta. So the magnitude of u times the magnitude of v times sine theta, that's the magnitude of your cross product term in the n hat direction. What is n hat? N hat is in the direction that is normal to the plane that the UV vectors lie on. Okay, so we're going to simplify this, and we're going to build vectors that are just along the xy plane. So we know for sure in that case that the n hat term will be in the k hat direction or the z direction, either into or out of the screen. Okay, and I'm gonna try to do the right hand rule. I know that my video is mirrored here, so I'm gonna try to use markers to give you an example, but I'm going to be looking directly at the screen, so I'm going to at least try to verbally tell you what I'm doing. So we use the right hand rule to determine if it's positive or negative. If it's coming out of the screen or the page on your paper, that's considered positive. It's going into the board or into the screen or into the page, then that's considered a negative value. And it's important that we recognize if it's positive or negative, because this equation itself does not capture it. This equation does capture it, but this one does not. And we'll see an example of how to actually apply this. So we'll take a look at the same 4 vectors that we looked at just a second ago when we looked at the dot product examples. And so here again we see all 4 vectors and their relationship to the u vector. So we're going to take a cross product of v, w, and z with respect to u, and we're going to see the effect that the order that we say the cross products have and that the angles have. All right, so remember, cross products, you can think about it as a torque or moment component, right? So there's a force piece, there's a displacement piece, just like in work, but in this case, you're looking at a moment or a torque, rotational effect due to it. And the cross product vector is a representation of that rotation. All right, so first we're going to look at a perpendicular set of vectors, the u and v vector, as we see right here. Right, so we found the vector and magnitude of it from the previous example when we look at dot products. And to help us to understand what the cross product is going to look like, we build the determinant right here. And we're going to build each of these components. So for I hat, we go 0, 0, minus 0, 3. For j hat, we go minus 5, 0, plus 0, 0. For k hat, we go 5, 3, minus 0, 0. And as a result, right, all of that shows up right there. We're going to get a 0 term for the I hat, 0 term for j hat, and 15 for k hat. So our result is 15 k hat. What you'll find is you'll always get 0 I hat and 0 j hat. And why is that? Well, you're on this xy plane, so the result has to be in the k hat direction. All right, so this is one way of solving for this cross product. The other way is this method right here. So I took the magnitude of the u vector, 5, times the magnitude of the v vector, 3, times sine theta. Theta is 90 degrees, as we can see right here. Sine 90 degrees is 1, so this will just be 15 n hat. And we know it's in the z or k hat direction. Now, how do we determine if it's positive or negative? So again, this is going to be, I think, reversed. So I'm going to try to do this in a way that makes sense. So let's say this is my u vector. I know it's pointing in the opposite direction. But I'm looking at the screen, so I'm going to just mirror what I'm doing. So this is the u vector, the first vector. You point your fingers towards it. So it's either this way or this way, right? So I'm trying to figure out which direction I want to point my fingers. The way that we figure out which way we point the fingers is which way is going to help me curl my fingers to my second vector. The second vector is vertical right there. Let's see, all right there, okay. So I can curl my fingers here and I'm going to hit it, and this is pointing out of the screen. So that's going to be in the positive direction. If I'm pointing my fingers this way and I curl, I'm not going to hit, I only hit it if the vector was pointing downward instead, right? So that's the way to use the right hand rule. So one thing to pay attention to is when you're in class and you're taking an exam, if you're like most people and right-handed and you're writing with your right hand, don't use the right hand rule with your left hand, because everything will be reversed. Hopefully that video demonstration with these markers was not confusing. I know the screen is mirrored, so just make sure when you do the right hand rule, you get that your thumb is pointing in the direction out of the screen for this problem. That's what you should expect. Now, what happens if I flip the order? If I switch it from U cross V to V cross U, what you'll find is basically these swap. Basically, you have a sign switch for each of these terms. All of these will switch, basically because, and you could redraw your determinant matrix. So it's 0, 3, 0, 0, oh, sorry, 5, 0, 0. And what you find is this gives us a negative k hat component. And you can do the same thing, right? So if I look at my vectors again, and I point in the first vector, v direction, so I'm either pointing this way or this way. So if I point this way, I don't hit it. If I point this way, I do hit it. Now my thumb is pointing into the screen. So that'll be a negative value. So that's how if I redid this problem this way, I would get a negative 15 k hat. Okay, so that's the case when the vectors are normal to each other. What happens if they're parallel or pointing in the same direction? So there's my w vector, and there's my u vector terms, and there's my w vector terms. If I do u cross v, I'll get 0 for the I hat component, 0 for the j hat components, and what we'll find is we get 0 for the k hat components. And so where does that come from? We'll go 5, 0, that's right there, minus 0, 3, right there. So this comes up to 0. So what does that mean? Well, when I tell students, think about the rotational components of it, it's almost like you're pressing into the hinge of a door. You're pointing right all along the length of the door versus pushing against an angle. So if this is the thing that you're trying to hinge across, if I push directly on in line with it, it's not going to rotate. If I push at some angle, it will rotate, right? So that's what the cross product is helping us understand. So for parallel components, it will always give us a cross product equal to 0. And we can see that resulting here with the sine component, sine of 0, because the angle here is 0. Sine of 0 is equal to 0. So we get 0 k hat. And it doesn't matter if you do u cross w or w cross u, obviously, you'll still get that 0 term. All right, let's do it for this last one here. For the z vector, we're at a 45-degree angle, and we can rebuild this determinant matrix again, 5, 0, 0, 3, 3, 0. Okay, so we take the cross product using this rule. We know that the I hat and j hat terms are going to be 0 because it's along that same plane. So the normal vector has got to be either positive or negative z axes. So I can just focus on the k hat terms, these terms right here, right? So I go 5, 3 minus 0, 3. 5, 3 minus 0, 3. This gives me 15 k hat. My angle is 45 degrees, so I can solve it in this form. The magnitude of u times the magnitude of v times sine 45. So magnitude of u is 5, magnitude of z is 3 root 2, and sine of 45 is 1 over root 2, or root 2 over 2. And so again, we get 15 k hat. And we can flip u and z order, and as expected, we get the negative of it. So we learned the dot product, which gives us a scalar, and now we've learned the cross product, which gives us a vector. The next step is to now go beyond just two vectors interacting. We'll take a look at what happens when you take a vector and you multiply it with a matrix. And we'll talk about why you might want to do this, what it could represent. And when you multiply a vector and matrix, do you get a matrix? Do you get a vector? What do you get from it? So that's the next step of discussion.